Okay, so welcome to this talk. And the speaker today is Noemi Stan, who has been a PhD student in the last 4 years now. She's finishing the PhD under the supervision of Cristobal and myself on different applications of complex system techniques to climate processes. And today she will talk us about what is the Madden Julian Oscillation and how to model it. So go ahead, Noemi.
Okay, thank you. Just gonna put this here. All right. So the title of my talk is the Madden Julian Oscillation as skeleton model with time-dependent observation-based forcing. And I will start with some overview of what the Madden Julian Oscillation is. So I'll just call it the MJO. So the MJO is a large-scale weather system which propagates in the tropics, so at the equator. And it consists basically of two parts. One part is enhanced convection, so that's like stormy and wet weather. And the other part is suppressed convection, so the opposite, sunny and dry weather. And with those convective anomalies, there are also like wind anomalies and pressure anomalies and so on. And this whole system propagates around the Earth at the equator in around 30 to 60 days. And when it travels, so when it comes to different regions, it affects the weather around the globe. So this is a figure from the first paper on the MJO, the paper from Madden and Julian. And basically, they just showed the evolution and the propagation of this system. So we see here the formation of the convective cell. This is on the Indian Ocean, more or less. Then we see that this convective cell starts to grow, and then it propagates to the east. And then it starts decreasing when it comes to the Pacific. And they also showed in this figure the circulation anomalies and the pressure anomalies that are associated with this convective system. So there are other aspects that I want to comment on this MJO. So first is the geographical confinement of the convective activity. So this is basically what I just showed. The convective center of the MJO is more active from the Indian Ocean to the Western Pacific, not really around the rest of the globe. Then the MJO is a very slow wave compared to other atmospheric waves. So it has an eastward propagation speed of about 5 meters per second. Another important point is that there's an intermittent generation of MJO events. So this means that the MJO wave is not always the same, but sometimes it's stronger, sometimes it's weaker, and sometimes it's so weak that we just cannot say that the MJO is active, so there's no MJO. So this intermittency is an important point. And finally, the MJO is an envelope of smaller scale convection. So the picture that I showed before is very idealized, but in a more realistic picture, if this is the MJO, then within the MJO, there are super cloud clusters. And within those super cloud clusters, there are other cloud clusters. So it's a very multi-scale structure. Okay, and then, like I said, the MJO has an impact on weather. So in the tropics, it affects the monsoons and the tropical cyclones in this region. Then it also tends to generate waves that propagate to the north. And when they propagate, they can affect weather in the mid-latitudes and typically blocking events. And then when it comes to the Pacific, it interacts with El Niño southern oscillation. So the point here is that a better representation of the MJO in the climate model would greatly improve the predictability of many of these phenomena. And this has motivated many people to develop simplified model to study the physical mechanisms behind the MJO. And we are going to use one of these models. Okay, so So I'm going to first present the model that we use, which is called the MJO skeleton model. And then I'm going to present the stochastic version of this model. And then so far, this model has mainly been used with very simplified and time-independent forcing functions. And the specificity of what we do is that we're going to use more realistic forcing functions in the model. We're going to use observation-based and time-dependent forcing functions. So I'm going to explain how we do that. And then I'm going to show what are the outputs of the model when we force it with those functions. Then I'm going to explain how we identify the MJO events within that output. And then finally, we're going to compare the characteristics of the MJO in the model and in observations. And we're going to see if we can detect the influence of El Niño on the MJO within the model. All right. So the MJO skeleton model was developed by Maida and Stachman in 2009. It's a minimalistic model reproducing the MJO skeleton. So by skeleton, they mean the planetary scale features of the MJO. So like I said before, the MJO is a multi-scale system. And in the model, we are only going to represent the envelope of the convective activity and none of the small scale details within that envelope. So it's the dashed line that is represented in the model. So those are the equations. There are essentially two parts in this model. The first part are the primitive equations. So they are like standard equations that are used to model the dynamics of the atmosphere. And they consist of conservation equations for momentum. So U, V, W are wind velocities. There's also a conservation equation for the energy. So theta is the potential temperature. And the conservation equation for the moisture. So Q is moisture anomaly. And then there's this equation, which is the addition from Maida and Stachman, and it's the key to be able to represent MJO waves. So it's a dynamic equation for the convective activity. So just to explain this in a bit more details, the key mechanism that is represented in this equation is that, well, first the variable. So A is the envelope of convective activity. Gamma is a parameter. Q is the low troposphere moisture. And so the mechanism that is encoded here is that a positive moisture anomaly creates a tendency to enhance the convective activity. And the reason behind this equation is that it's been seen in observation that the lower tropospheric moisture leads the convective activity. So this is the motivation for this equation. Okay, so this is the system of equation, the first one, the first version of the skeleton model that was presented. And then there has been like several modifications and improvements to this model. And one of them is to make this equation stochastic, because if we keep the equations in this way, we have a deterministic model which is able to produce waves with MJO characteristics, but there's no variability in the MJO. So so this is not really realistic, because like I said before, the MJO is not always the same. Like sometimes it's stronger, sometimes it's weaker, sometimes it's there, sometimes it's not. And so in order to create that variability, these people, Tual and other, in 2014 have proposed to make A stochastic variable, which is controlled by a birth-death process. And so this is the master equation for this. And basically, they just chose the up and down transition rates in this equation so that on average, we recover the original equation. So this is the model that we're going to use. And we just have to remember that our model is stochastic, and the stochasticity comes into this equation in the variable A. Okay, now some comments on this model. So first, it has a very few number of parameters. So there's this gamma, which I already commented, which is the sensitivity of convective activity to moisture anomalies. Then there's this Q tilde, which is mean background vertical moisture gradient. And then there's H bar, which is a scaling constant for convective activity. So those are the only 3 parameters in the model, and we choose for them standard values that were used in the previous papers on this model. Then there are 2 forcing functions. One is radiative cooling, so that's the heat loss from the Earth by radiation. And the other one is latent heating. That's the heating due to phase change of water. So for instance, if water droplets condensate in the atmosphere, then it releases some heat. So this is this forcing. And and then for the implementation, we need to simplify this set of equation. And what we're going to do is do a vertical and meridional. So meridional is north-south. So we do vertical and meridional truncations, so that in the end, we only model amplitudes on a one-dimensional line along the equator. So our model will be on this line, and all the results, everything that I will show will be on this line here and not 3-dimensional, 2-dimensional. Okay, so like I said, in previous studies, the forcing functions, so the radiative cooling and the latent heating, were mostly chosen to be mathematically very simple and also time independent. And the specificity of what we do here is that we're gonna compute these functions based on observations, and we will let them be time-dependent functions. So so this is like a way more realistic way to force the model. Okay, so in order to compute these functions, we use the methodology which was presented in this paper. So for SQ, we used observations of latent heat flux, and for S theta, we use observations of latent heat flux and precipitation. And the data is monthly data over this period, so that's 42 years. So essentially, we obtain a forcing profile every month for 42 years. No, the time step of the model is much smaller. It's a couple of hours. So we interpolate the forcing profiles to the time step of the model. And then, so like I said, we have time-dependent profiles, and we just move them with a 3-month moving average so that there's no too sharp changes in the forcing. So this is what they look like. So this is for S theta and this is SQ, and then in horizontal, we have a one-dimensional line along the equator. So this is the line that I was showing basically. So it's here on this line. And then this is for 1 year. We have 42 years of forcing, but I just showed the first year of the forcing profiles. And so what we can see is that there are some variations between winter and summer. And also we can see that the 2 functions are quite similar. And the reason behind this is that, I mean, it's a bit technical, but there is a condition in the model that S theta and SQ, or I mean, like this equality should be satisfied. And so we compute them in a way that to make sure that this is satisfied. And that means that they're not really independent from each other, and that's why they look like this. Okay, so we force the model with these functions, and we get some output. So we get information on the wind, the moisture, the potential temperature, and the convective activity. And here I just show the evolution of the convective activity in the model. So on the left, this is the, say, raw output data. So this horizontal is again the equator line, and this is 1 year of simulation. And what we can see here is that we have more activity in this region from, say, 60 to 220. And this corresponds indeed to the region of the MJO. So 60 is more or less in the Indian Ocean, and and then like above 200, it's in the Pacific. And then in this figure, what I show is the same data, but if we filter it using keeping only the frequencies between 3 weeks and 3 months, which is where we know that the variability of the MJO is, and also keeping planetary scale waves, so waves that have a wave number smaller than 4. So this is what we get, and then we start to see some propagating waves. For instance, here we have something moving at 6.6 meters per second to the east, so this is more or less the speed of the MJO. Here we have other waves, and some of them are moving westward here. Okay, so so then we can look at the long-term average of observed and model convective activity. So observation is in black and the model is in red here. So this is the average along in time. So it's like if we take the average in that direction. And we see that they agree very well. Then we can also compare the variance of the convective activity for the model and for observations. And here we see that the agreement is not that good. So the model overestimates a lot the variance. But then if we keep only the first 14 spatial modes of the model output, so that's like the waves, the large scale waves, right? Then there's a much better agreement. So we can say that there's good agreement between the convective activity in the model and observation when we consider planetary scales. And this is, first, this is fine because the MJO is a planetary scale wave. And also this is maybe not expected, but this is, this could be explained by the fact that the model was designed to reproduce planetary scale waves. So it might make sense that it doesn't reproduce well waves with high wave number. Okay, so now we need some way to identify the MJO events, the MJO propagating waves within this data. And to do that, we use an index, which is called the real-time multivariate MJO index. This index allows to keep track of where the MJO is and how strong it is. And there are many other indices, but the big advantage of this one is that it was developed both in the model and in for observations. So it allows us to make comparisons between the characteristics of the MJO in the model and in observations. That's why we choose this one. So to compute this index, we need some data. We take the wind and the convective activity that come as output of the model. And then there are a few technical steps. So first we need to compute the anomalies of the data. Then we filter the anomalies by using a Lanczos filter, and this is to isolate the intrasignal signal in the data. So that's like the waves that have frequency from 3 weeks to 3 months, which is the variability of the MJO. Then once we have filtered the data, we compute the empirical orthogonal functions of the combined fields. And that gives us some spatial patterns, which I've shown here. So basically, those patterns, they represent the dominant pattern of variability in the data on intraseasonal timescale. And then we project the values of wind and convective activity, so the original data, onto these two patterns. And so that gives us 2 time series, which we call RMM1 and RMM2, and together they form the RMM index. So the projection essentially serves as a way of filtering the MJO activity within the data. And this is what the time series look like, just as an example. But this might not be the best representation of that index. And a better way to show it is actually to plot the values within a diagram where RMM1 is in the horizontal and RMM2 is in the vertical. So here I've shown 52 days of simulations. So each point corresponds to the state of the MJO on a given day. And then the distance of that point to the center gives the amplitude of the MJO. So usually the common definition is that the MJO is active, or that there's an MJO event if the amplitude is larger than 1, and this is shown by the circle. So all the dark blue dots correspond to one single MJO event. They all lie outside the circle. Then the other good thing about this diagram is that it shows where the MJO is. So the eastward propagation of the MJO is shown by the counterclockwise propagation within the diagram. And each, we have divided it into 8 regions, and each corresponds to a different region on the globe. So we know that if the points are in this region, then, for instance, that means that the convective center of the MJO is within the Indian Ocean. And then if it's here, it's in the maritime continent, which is basically the Philippines and over there. And then if it's there, it's in the Pacific Ocean, and so on. So using this type of, using this index and this type of diagram, it's very easy to identify different characteristics of the MJO events. So for instance, we can compute their duration. It's just the number of points between this one and this one. Then we could compute the total angle covered by the RMM index in phase space. So that would be the angle from this point to the last point of the event, which is roughly a measure of the distance covered by the MJO. And then we can compute the maximum of this index. So the maximum amplitude, which in that case would be somewhere around here. So what we do is that we use this index to identify MJO events in observations for a period of 42 years. And then we use the same index to identify MJO events in the simulation when the simulation is forced with over the same 42-year period. Then we compute these 3 characteristics for all the MJO events that we have found, and we compare the characteristics in observations and in reality. And this is what we obtain. So we have the 3 characteristics: the duration, total angle, and maximum RMM amplitude. We show their cumulative distributions, and the black line represents observations, and the dashed line is for the model. And so we see that we have very good agreement for all 3 of them. So basically it says that the model reproduces well the statistics of the MJO events, or these statistics at least. Then another thing that we can do is count the number of MJO events that we obtain for each month of the year to see if there is some kind of seasonal cycle. And when we do that for observations, we see that we have more MJO events during winter month and less MJO events in the summer, boreal summer. And for the model, there's no difference. So there are several reasons that could explain this. One of them is that because we average the forcing over 3 months, then we kind of smooth the differences that we have within the seasons. So that it could be the reason, but there are other things. Okay. Then the last thing that we do is that we look at the influence of ENSO on the MJO characteristics in the model. So El Niño Southern Oscillation is an irregular oscillation which affects the winds and temperature in the tropical Eastern Pacific Ocean, so here. So when the temperatures are colder than normal, this is a La Niña event. And when they are warmer than normal, this is an El Niño event. And the question that we ask is if the skeleton model can capture some of the influence of ENSO on the MJO events. So to look at this, we look at the same characteristics as before. but we separate the MJO events that occur during the neutral phase of ENSO, during El Nino, and during La Nina. And then, same as before, we look at the cumulative distributions of these events characteristics. And what we see is that they agree very well in all three cases. So basically, the model does not identify any differences in duration, distance, and speed. That's not speed, maximum amplitude as a function of ENSO. Okay, so as a conclusion, we can say that the MJO skeleton model forced with observation-based time-dependent forcing functions captures several important features of the MJO. That the model reproduces well statistics of events duration, total angle covered, and the maximum of amplitude, but it does not capture the seasonality of events. And then also the model does not identify differences in the duration, distance, and maximum of amplitude as a function of ENSO. And this is fine because it's a very simplified model, but it was interesting to check anyway. And that's it. Thank you.
Okay, thank you. Thank you, Noemi. So now the paper is open for questions or for comments. So just unmute yourself and you can ask directly questions to Noemi. If not, just to start, I have a number of questions, Noemi. Just one of them. You have well, in the model, the convective activity is a variable in the model, but how is this measured in reality? Could you explain a little bit how this convective activity is measured in reality, not in the model?
Yeah, so the convective activity is related to clouds. So let me just come back to this picture because I think it shows it well. Oops. This one. Okay. So the convective activity essentially can be associated with the quantity of clouds. And so one way to measure it is to measure the radiation using satellites, the radiations that come from the Earth. So this is called outgoing long wave radiations. And basically, if we measure like a negative anomaly in these outgoing long wave radiations, then we know that there are lots of clouds, and so we can associate that with the convective activity. I think there's other paper also, like the paper that I showed to compute the profiles. This one, which also argues that you can compute it from precipitation. So there are different ways to estimate it, but I think those are the two common ways.
Okay. I have a question. Thanks, Noemi, for the presentation. So within the model, there are no differences between El Nino and La Nina. Can you summarize the real differences observed in reality? Yes, a bit summary.
Yeah, so I think, so one of the main differences is that it seems that during El Nino, the MJO propagates further to the east than during La Nina. So this is like more a spatial difference. And I think this is one of the key reasons why the model cannot represent this. It's because we've seen I didn't show it in this presentation, but we have seen that the model is not very good at representing like the spatial characteristics of the MJO. So this is related. And then there's also a different thing, which is that another aspect is that the MJO has been seen to propagate faster during El Nino than during La Nina. So this is probably due to the temperature of the sea. I don't know. Good.
Thank you.
More questions or comments? I have another one, is that your contribution to this has been to introduce the time-dependent and spatially dependent forcing. can you comment a little bit what happens if the forcing, you do the same, but with the forcing being time independent? Which things are better with your results, or which things are not reproduced just using a time independent forcing?
So I think okay, there are two different things. Like I think one is the computation of the profiles based on observations, and the other one is to keep the time dependence. So I think that actually, if we compute the profiles based on observations, I'm not sure that it makes much difference to do them time dependent or time independent. But if we keep like simple functions that are not based on observations, instead of using observation-based functions, then we've seen that we have to choose a different or slightly different parameters so that we can reproduce exactly the characteristics of the MJO. That's the first thing. And then I think some of the characteristics would not be as well represented, but I'm not sure. Yeah.
Okay. Any additional question or comment? If not, then let's thank Noemi again. And that's it. So see you next time.
See you.
Okay.
Bye.
Goodbye.
Thank you, Noemi.
Bye.